last time we ended by talking about power. I plan to give that a little bit of practice today before we switch gears and move on to something new. Any questions or objections to that plan before we get started? All right, a further reminder, no lab this week. You hadn't heard that yet, which includes today. There is lab next week though. So, tail end of chapter 7 is what we were covering yesterday. We've talked about work done by friction, efficiency, and now last thing that we covered was power. Power is the measurement of the rate at which work is performed. Power equals work over time for that reason. And what are words? You can think of power not only as the rate at which work is performed, but also the rate at which energy is consumed. A higher power rating appliance should get more work done in a short amount of time, but it also uses more energy in that shorter amount of time. We measure power in watts. 1 watt is 1 joule per second. That is 1 joule of work done every second. Also 1 joule of energy used up every second. A 20-watt light bulb needs 20 joules every second of electricity in order to stay on. If it doesn't get that much energy quickly enough, it gets dim or just goes out. So that's true of the wattage for every appliance. A 1,000 watt refrigerator needs 1,000 joules of electricity every second, or your ice cream melts. So note that whenever you are appliance shopping. Higher wattage does mean higher power, like more effective at getting its task done, but it also will drive up your electricity bills. Buy low wattage light bulbs. And before we close the book on chapter 7, I wanted to give you guys just a little bit more practice to apply the formula and the concept real quick. So, to that end, we are going to have 2 people lifting heavy things up a flight of stairs. Each of these 2 people is going to lift something vertically a distance of 30 meters. So, poor scale drawing of 30 meters worth of steps. That is 30 meters up, and the up is all we really care about here. Each of these 2 people are going to be lifting heavy things, and it is your job to calculate both their work output and also their power output. These 2 humans, human number 1 is going to carry a 1,000 Newton box that is already its weight pre-calculated. Human 1 also is going to run up these stairs in 1 minute. Human 2, meanwhile, is going to carry a smaller 500 Newton box. Again, that is its weight. They are going to do so in half a minute. So, I'll put it to you guys to work either on your own or amongst yourselves for a second. I want you to tell me the work done by each of these people, which one does more work, and then separately the power output of each of these people, which one is more powerful from a mechanics physics perspective.
Those are the same thing.
Same power output. All right. Any objections to that statement? All right, no objections. Yes, ultimately they will have the same power output. Before we get to that though, do they have the same work output? No. Formula for work is still force times distance. Person 1 is going to have to exert at least 1,000 newtons of force vertically for a 30-meter displacement. So 1,000 times 30, person 1's work. Person 1 outputs 30,000 joules of work. Meanwhile, person 2 uses half as much force for the same distance, so their work output is half at 15,000 joules. So they don't have the same work output, they use different amounts of energy, but person 2 does half the work in half the time. And that is ultimately going to give them the same power output, the same wattage. Power is again work over time. So we would take each person's power and divide it by the time it took them. Person 1 did 30,000 joules of work in 1 minute. How many seconds are in 1 minute? So then 30,000 divided by 60, not divided by 1, is 500 watts. Then person 2, how many seconds are in half a minute? Not a trick. 30. And 15,000 divided by 30 is also 500 watts. So each of these people have the same power output when it comes to lifting these heavy things up the stairs. A couple points I'd like to illustrate here. Just from the physics perspective of power, speed is as important as muscle output. If you can do something quickly, that's often as good, sometimes better, than just being able to punch hard. To kind of illustrate that point, again, I do a lot of Taekwondo examples in here. It was a very formative part of my childhood. Taekwondo, as a martial art, was developed in Korea, and statistically speaking, it was invented by pretty short people to take down very tall people who were invading from the north, historically speaking. And as a result, the art style of Taekwondo is really focused around dodging and striking hard and fast with your kicks while your bigger opponent is bewildered. You might not have as much force output as your bigger opponent, but as long as you aren't getting hit and can kick them several times very quickly, that is as good as one strong punch, if not better. So again, speed is important. Speed can create a very powerful output. Additionally, if you ever wanted to know your own power output, you could do something similar. Basically, if you know your own weight and you know how quickly you can run up a certain height of steps, you can do this process to find your own power output. You could convert watts to horsepower then if you wanted to. I did a lab when I taught at a different school where students would do that if they wanted to, calculate their own power output. Some of the athletes actually did come out to about 1 horsepower. I'm at like half a horsepower. So that was just all the points I think I wanted to make with this one. As application of the power formula, how do we feel? All right. So with that said, that is everything I wanted to cover from chapter 7 done. Now, my original plan when working out the schedule this semester was to try to get through all of chapter 7 before test 1. That just didn't end up happening. Just calendar and schedule stuff. It's always like trying to play darts on a moving train. So some of these chapter 7 things just got pushed over to after the test. My original plan was for test 1 to kind of be the pivot point to the second half of the class. The second half of the class is, in my opinion, about weirder stuff. first half of the class is meant to be about normal, linear mechanical motion and the things that tie into it, stuff that you've been noticing your whole life. Okay, bad way of saying it. You still noticed all the stuff in the second half of the course your whole life, but in my opinion, it's weirder to think about. We're gonna start doing things like rotation, pressure, these invisible things that kind of affect your life that you still observe, but you don't think about as much. Eventually we'll move on to things like sound and electricity too. So now, with 7 done, even though this part came after the test, I do feel like this is still kind of the turning point. I'm not going to say things aren't necessarily going to get harder, they're just going to get weird, if that makes sense. Does that sound fair? All right. And the first weird thing that we will move on to is rotation. And this one might take us a minute, which is okay. I've allotted for it in my adjusted course calendar. Any questions or objections before we begin this new subject? All right. So, chapter 8, rotational motion. I want to throw out some vocab words real quick to make sure that these terms make sense when I start using them casually. Up until this point, all of the motion we've been describing has been linear in nature. And I believe I've said that word before, but just in case, to redefine linear, this word means of or referring to straight lines. That's why it's literally spelled line R. All the motion so far has been linear. It's just been forward or backward in a straight line. And so too have all of the forces and momenta. They're all just pointing in straight lines. So everything up till now has been linear. And I find that humans tend to think about the universe in pretty linear terms. Humans are usually pretty good at identifying and tracking straight lines. Rotation is a little bit different to that, because linear motion is not the only way that something can move. To try to illustrate my point, behold the disembodied bike tire of science, highly advanced tool. I'm going to hold the center axle in my hand, and I'm going to do this. Now, in your professional opinions, do you think this wheel is moving? All right. Do you think it is moving linearly? No. What is its current linear displacement? 0. It's not moving any number of meters in any straight line axis. What is its current linear velocity in those straight line XY axes? It's 0. It's not displacing over time either in any of those dimensions. We can agree that it's moving, but all of our linear terms are kind of failing to describe that motion. This is a different type of motion, and to that end, we need new terms to describe it. And so that is what the first part of this chapter is going to be about. Rotation is just a different form of motion, and kind of like how at the beginning of the course we went through displacement, velocity, acceleration to define how we describe those things, we need to redefine them for how they work for a wheel that spins instead of moving in a straight line. So the beginning of this chapter is going to be redefining motion from the rotational perspective rather than from the linear one. Sound good so far? All right. Now, before I do that, there's one more vocab word I want to mention because I'm going to say it a lot and I want to make sure that it makes sense. I interchangeably use 2 different words for rotational motion because I was taught both of them and my brain now uses them interchangeably. And I think your textbook does as well. Again, linear is what we've been doing, straight lines. We're moving into rotational, again, relating to the rotation of an object rather than it's moving in a straight line. The term angular is a synonym to rotational. Rotational is talking about rotation. Angular, the word itself actually means of or referring to angles. Ignore the U, angles. Which means the same thing. If something is rotating, it is rotating through a number of angle degrees, correct? So these two words, rotational and angular, are synonyms. And because they are synonyms, I'm gonna kind of use them interchangeably. And just the way my brain works, if two things mean the same thing, whichever one comes out of my mouth is just kind of a coin flip. So I want to acknowledge here now, whether I say rotational or angular, I'm referring to the same thing. And I believe your book, if you've been following along in the book, does the same thing as well. It uses both terms to describe this type of motion. Additionally, just to kind of point out where you've seen this before, everything labeled angular on the formula sheet is referring to this rotational stuff. So if it's called angular on here, that's what we're covering in this week and a half. So, just disclaimer, you'll be hearing both terms from me. Does that sound okay? All right. Okay, now, we agreed a second ago that spinning wheel is moving, but since it's not moving in a straight line, we can't really define its motion as delta x measured in meters. We need a different metric for it. So, first thing we're going to talk about is angular displacement as opposed to linear displacement. If you recall from the beginning of the course, we've been using delta x or delta y to describe linear displacement, the distance something moves in a straight line. And we would measure that in things like meters and feet. To instead describe the rotation of this wheel, we need a different metric, a different variable. So instead of linear displacement, we use angular displacement, or again, rotational displacement, synonyms. So this is a new variable. It is similar to but distinct from linear displacement. So this here is angular displacement, and that is delta theta, Greek letter theta, which should sound familiar. If for no other reason than geometry class. Dang it. Does that look familiar? Has anyone not used this in a geometry sort of thing before? All right. In your past math and geometry classes, anytime you were looking at some unknown angle, there's a chance you might have labeled that angle as theta. This theta is the same thing. In math, in geometric type math stuff, we use theta to describe some angle rotation from one point to another. And so this new variable for physics is the same use of the letter. In physics, rather than, if something is spinning, rather than again measuring how far it moves in a straight line, you measure how much it rotates, how many angles it rotates through, or how many degrees it rotates through. So if something is spinning, you would measure its angular displacement using delta theta, and instead of units like meters or feet, you would use a unit that describes rotation. And there's actually a couple different measurements for that, a couple different units for angular displacement. To try to illustrate this application, I'm going to take the bike wheel. Here we go. Note here where the air valve is. This little black piece here. I am going to start this wheel basically with this at 12 o'clock, and I'm going to further put my hand here just so that you can also track where my hand is. And I am going to make this wheel rotate a certain amount. I would like you to describe to me the magnitude of the angular displacement that I make this wheel spin through. All right? So, first turn, we're starting at 12 o'clock, and I'm rotating to here. What is the magnitude of that angular displacement? 90 degrees. That completely describes how much it spun. Degrees is a unit for angular displacement, just 90-degree angle. That is one of the units. There's actually a couple different ones that will be used somewhat interchangeably at times. One unit for rotation is actually just number of rotations. You can use rotation as a unit. So how many rotations is this in units of rotations? Quarter turn, exactly. So you can describe this as 90 degrees as a quarter turn. Those are the two most common units outside of physics class. There's a third unit, and I want to make sure to address it now because it will come up. Again, kind of flashing back to geometry classes. That third unit is radians. The relationship between degrees and radians is similar to that of meters and feet. They are two different ways to measure the same thing. And I've got the relationship between all three of these things on the board right now. One full rotation is at 360 degrees, and both of those are equal to a number of radians equal to 2 times the number pi. So this is just a different unit than degrees. 360 degrees is equal to 2 times pi radians. The pi is not a unit there, it is a number. It's a part of the measurement here. If you were to actually calculate this number, 2 times 3.14, you get 6.28 radians. I'm hoping this sounds like review. It's just a different unit for it. So one full rotation is 2 pi radians. Therefore, if I instead asked you to measure this rotation in radians rather than degrees or rotations, how many radians is this?
Pi.
0.5 pi, precisely. 2 pi is one full rotation. That means that half a rotation is just pi, and therefore a quarter rotation is half of pi. Pi over 2 or 0.5 times pi. Again, there's just 3 different ways of saying the same thing. Quarter turn, 90 degrees, pi over 2 radians. I only bring up all 3 of these units because different questions are going to ask you about different units. Sometimes you'll have to use one over the other. For example, most physics formulas actually take radians rather than degrees, as it turns out. So I want to talk about them all now because you'll be using all of them to various capacities. But this is how we measure angular displacement. It's just how much has something turned. And we have 3 different units to describe it, to measure it. Sound okay? All right. Now, next thing I want to discuss. At the beginning of the course, we went through several variables to describe motion. We have delta x for linear displacement, and then we also had v for linear velocity, describing how quickly something displaces. You can do that with a wheel too. Delta theta is how much it turns, but then you can also figure out how quickly something is turning. And the way that we describe that in physics is by measuring its angular speed or angular velocity. Since the direction doesn't really matter as much, you can only really spin forwards or backwards. Speed versus velocity is less important when talking about spinning. But just like how displacement over time linearly gives you linear velocity, you can take angular displacement divided by time, and that will tell you angular speed or velocity, how quickly something is spinning. And you actually look at an angular speed measurement every time you drive a car, because most cars have an RPM meter, rotations per minute. Rotations is a unit of angular displacement, and minutes is a unit of time. So RPM, rotations per minute, is measuring the current angular speed of your tires. So again, it's not, I'm hoping not unfamiliar, even if you haven't thought about it this way. So this is the formula we use for angular speed, angular velocity. And I really want to drive home how similar it is meant to be to the linear velocity formula, because the definition of velocity didn't change. It's still displacement over time. It's just, instead of meters linear, we're looking at rotations angular. It's the same structure to the formula, it's just replacing the linear stuff with the angular stuff, with their angular counterparts. These two formulas are basically mirror universe twins of each other. I tend to describe a lot of the angular stuff as a mirror universe copy of the linear stuff. I'm hoping that point will be made clear as this chapter goes on. But angular displacement over time will tell you current angular speed of a rotating object. Since it's not the same thing as linear speed, it has its own unique new variable, like how angular displacement has its own unique new variable. But this one might be less familiar than theta is. This letter, it's technically not a W, it's technically lowercase omega. Uppercase omega is the horseshoe, lowercase omega is this funky looking W, this weird mustache looking thing. If you want to call it W, you can, I won't fault you for that. Because it's technically omega, and because there are other W's on the formula sheet, I'm going to say omega equals theta over time if I'm reading this one out loud. So if you hear omega from me, that's what I'm referring to. But you could call it W, you can call it mustache if you wanted to. Whatever helps it stick in your brain. And again, it's just the slightly weirder Greek version of the linear motion formula. And the units for angular speed kind of just depend on what units you put in the formula. You could put in rotations and minutes and you get rotations per minute. You could put in degrees and seconds and you get degrees per second. So it's very important to track your units. Track which ones you're given, track which ones the formula would give you as a result. Because again, this is one of those measurements where the unit just kind of depends on what you know and who's asking. Because in America, we do tend to like rotations per minute, but the metric system tends to prefer radians per second. So again, just note the units you're given. How it feels so far. All right. With all that said, let's get a little bit of practice in for this before we head towards close for the day. We are going to take a wheel and we are going to make it spin 180 times in 1 minute. So just wheel, you'll get it spinning, and then through some system you are able to clock that it rotates 180 times within a 60-second time window. And 2 pieces of information given. My first question, what is the angular displacement of the wheel at the end of that 1 minute? What is the angular displacement of this wheel? Rotational displacement of this wheel.
180
What would the unit be?
rotations.
Yep. 180 rotations is a completely accurate way to answer this question. Because angular displacement is, again, how much did it spin? And it spun 180 times. So that is an answer. Number of rotations is an answer to angular displacement. If I don't specify a unit, that's an answer. Now, for practice sake, I do want to convert that into the other 2 common units real quick, just to show how that works. This is an answer, bless you. This is the number of rotations that take place. But just to demonstrate, we can convert number of rotations into number of degrees. Again, I've got over here, 1 full rotation is 360 degrees. So basically, if we multiply by 360, we can find how many degrees the wheel is going to spin through. I'll just show the way that I usually do conversions. I believe that is 64,800. So that is the answer specifically in units of degrees. And we could also convert that into radians. In which case, 1 rotation is 2 pi radians. And again, pi there is part of the number, it's not a unit. So if you put this into your calculator correctly, it would be 180 times 2 times pi. Rotations cancels and leaves you with radians. You could write that as either 360 pi radians, or alternatively, if you multiplied the number pi into 360, you'd get 1,130.97 radians. Both are acceptable answers, just depending on whether you factor the pi in or you leave it by itself. So there are 4 ways to write this answer, and unless I ask you for a specific one, I would count all of them as correct. If I haven't said this yet, I tend to shorten radians to just rad. Sometimes I shorten rotations to rot. So for this first part, how's that feel? All right. Next question. What is the wheel's angular velocity given this information that's spun this many times in 1 minute? How could you describe its current angular velocity?
Three rotations per second.
3 rotations per second. That's a pretty good way to say it. So omega equals delta theta over time. If we went with 180 rotations, again, rot for rotations, and 1 minute is 60 seconds, 180 over 60 would be 3 rotations per second. Noting again, the unit should be constructed based on what units you put in. So this would be rotations per second. Depending on who you ask, like say a car enthusiast, they might have left it in minutes and just said 180 rotations per minute, which is also correct. But that would be the correct answer in rotations per second. And you could instead plug in any other unit to get a slightly different answer. That said, just to practice it, what would specifically the answer in radians per second be?
Six pi.
6 pi. I'll just leave the pi in. We determined if we don't multiply the pi in, the radians displacement is 360 pi. Divide that by 60 seconds, and that would give 6 pi rad per second, which, if you did factor in the pi in your calculator, should be about 18.8, I believe. Both are correct, just depending on whether you leave the pi in or out. So that is a couple different ways to describe how fast the wheel is rotating. How's it all feel? Excuse me. Sorry. All right. So those are our 2 baseline metrics for rotational motion. We'll often be referring to angular displacement as how much something moves angularly, and then angular speed as how quickly is it moving angularly. Again, we're kind of reestablishing our new baseline, our new metrics for spinning instead of straight lines. Now, even though this is a new way of thinking about things, it doesn't mean we're throwing out the old stuff. The whole point of this course is that everything kind of builds on what came before. So I want to at least take a second to try to illustrate how similar rotation is to linear motion. On the left here, we've got all the linear motion formulas and concepts from the start of the course. We've got linear displacement by itself, velocity, acceleration, and then formulas 3 and 4 for displacing while accelerating. All of these concepts still exist in the angular way of thinking of things. They're just utilizing rotations and revolutions, rotations, radians, or degrees instead of meters forward. We're not going to have to cover all of these. You don't have to use all of these. There's more formulas on the formula sheet than you're going to need. For example, I don't think we're actually going to deal with these ones very much. But just again, to try to illustrate the similarity, these are all the same formulas. All the same concepts we've discussed for linear motion still work here. The relationship between displacement and velocity is still intact. Additionally, the relationship between acceleration and velocity is still intact, because angular speed can change. You can speed up or slow down while spinning as well. I'm only bringing this up to try to illustrate that we're not throwing anything out. We're kind of expanding the scope of our terms. We're going to take the logic we've already got for linear stuff and start applying it to the weirdness that is the rotation stuff. So I'm just trying to illustrate this is not going to be all new content. We're still building upon what we've already done. Any objections? All right. I do kind of view the linear and angular stuff as separate worlds in a way. Like, again, watch enough sci-fi, parallel dimensions, and this is the universe where everyone's evil and Spock has a mustache. See, mustache right there. Kind of furthering that analogy, you usually need a way to cross between the two worlds. It's all well and good if they just exist on their own, but there's usually some amount of crossover between the two. And that's true in the real world as well. Kind of going back from the analogy real quick. There's a bridge that needs to be made between these two concepts, because these two forms of motion do not always exist separately from one another. You can have linear motion by itself, something just moving in a straight line. You can also have angular motion by itself. That would just be something spinning in place. And that would be what happens if the two worlds just exist by themselves and don't ever interact with one another. But very often, we have scenarios where something can do both at the same time. That's kind of the entire purpose of a wheel, isn't it? It's to be spinning while also moving forward. Linear motion and angular motion are able to occur simultaneously. And that's what this middle part is here. I'm going to tab ahead and try to cut out the formulas you don't actually need. Just going to pare it down to the ones you need to care about right now. If linear motion and angular motion are taking place at the same time, again, like a wheel rolling forward while spinning along the ground, then the two forms of motion are kind of intersect. Because in the case of a wheel, how far forward it rolls directly depends on how many times it spins, right? If I try to roll this wheel across my desk, I'll, again, air pump right here at 12 o'clock to show the beginning. If I spin it only once, that's the totality of how far it can go. Its linear displacement is directly tied to its angular displacement. For a rolling item, they're stuck together. One is directly connected to the other. Similarly, the speed at which it is spinning will correlate directly to the speed at which it is moving forwards. Because if the wheel's spinning faster, if you pedal the bike harder, you will go forward faster. So even though the linear and angular worlds can exist separately, they're kind of irrevocably connected when the two take place at the same time. And this short list of formulas here in the middle exist to help you translate one form into the other. They exist to kind of illustrate the connection between how much something spins versus how far forward it also rolls. And so I call this short batch here in the middle the translation formulas. They exist to translate what happens in one to the other. For example, this one here in red, this exists to turn linear displacement into angular displacement. The purpose of this formula is to say, this bike wheel moved 3 meters forward. I can now calculate how many times it has to spin in order to make that happen. Because for every wheel, it takes a certain number of spins to make that possible. Same is true with the velocities here. If I know the linear speed, I could figure out the angular speed. If I want to be moving so quickly forwards, I need to be spinning so fast to make that possible. And so that's what these formulas in the middle are for. And similarly on your equation sheet, they're organized very similarly. We got the linear stuff here, rotational stuff here, and then the gap bridging translation formulas labeled between the middle. So I hope that makes sense visually. And the secret factor that helps you convert from one to the other is the radius of the object that is doing the spinning. The physical radius from center to edge of this tire. And that is what the R's are in those formulas. We've got delta theta equals radius times delta x equals radius times delta theta. V equals radius times omega. The radius of the wheel is what allows you to translate its rotational motion into linear motion and vice versa. And that's going to kind of be what we practice, what we move into next time as we start looking into how all this rotational stuff applies to physics as a whole. Just know that when I'm saying radius, the R up there, I do mean radius center to edge, not diameter, radius. And that's what we'll pick up next time. Questions, concerns? All right. Again, no lab this week. We have Wednesday lab. Make sure that you don't show up this afternoon. Take the day off. And have a wonderful day. Let me know if you need anything.